This is a video covering a walkthrough of the various physical parts of my relay computer, effectively a computer tour. And it forms part of a 2020 update series of videos, with this one being the 5th episode in that series. The first video covered the architecture of my relay computer, and then in my second video I covered the instruction set that the computer uses. To make programming easier, I created an assembly language and that was covered in the third video, and then in the fourth video I shared a worked example of programming the computer from idea through to assembly and then hand compiling into machine code. In the next and last video in this series, I'll take that program and load it into my relay computer to demonstrate it running through. So, welcome again to my relay computer. This picture is taken face on, and choosing those glossy panels is coming back to haunt me yet again. This time in the reflections you'll find a camera tripod, your narrator, and a Lego model of Tower Bridge. Although the panels are a nightmare to photograph, they really do look the business in person, so pros and cons and all that. Anywho, if I rotate the computer clockwise, here's the view from the right, back, left. And yep, there's still some cables hanging out the back, not as much as before though, but these will eventually join their siblings and can be neatly routed within the case. Speaking of which, you probably guessed the case is a half-finished job. Mainly that's to ease working on the insides for now, but eventually it'll be completely encased in black perspex, so it'll look a little bit like this. Both the front and rear covers are removable, and I'll show that now. If we take a closer look now at the front and rear, you can see that the enclosure is broadly split into two halves, the upper and lower enclosure. Focusing on the upper enclosure for a moment, we can see that it's broken into three sections. At the bottom are the primary switches, which is the main way that the computer is operated. These are accessible even when the front covers are on the computer. At the top left when viewed from the front is display A. This shows which control lines are currently being operated by the computer, but also allows the user to directly operate those control lines for debugging and testing purposes. Alongside this is display B, which shows things like the status of condition registers, current instruction code and class, LU operation, data and address bus values, and finally the amount of juice the computer is consuming. Here's a close-up of the upper enclosure. The buttons on display A are operated like this. And on display B, the LED elements look like this when operating. Operating the primary switches looks and sounds like this. Here's the upper enclosure seen from behind. There's actually less to see here as there's a whacking great power supply stuck in the way. Although visually obtrusive, this does of course mean that the computer can run under its own steam as it were. Mains power comes in on the IEC socket at 230 of our English Leicestershire volts, and then goes up to the PSU, which outputs 12 volts at 15 amps for 180 watts. From there the 12 volt goes over to the ammeter and then down to the power distribution board, which, as the name suggests, distributes the power to the card bays and displays. Finally, the ground line then comes up from the distribution board and back to the PSU. Whilst we're poking around the upper enclosure, there's also this curious little card peeking out from behind the transformer. This is a temporary mini card which uses a 32.768 MHz crystal to generate a clock signal. Now, that's a tad fast for the relay computer to use, but because 32,768 is a power of 2, we can run the signal through a series of divide by 2 gates, which will get it down to something more reasonable in the 0.5 to 64 Hz range. Using an 8-to-1 selector chip, I can pick off a specific speed using the dip switches. In practice, 64 Hz locks up the relays, so 32 Hz is the fastest I can reliably go. Eventually there'll be a proper clock card in the computer, but this will do for now. So that's enough of the upper enclosure. Let's focus next on the lower enclosure. The lower enclosure is split into 4 bays, which take 5 cards each. Viewed from the front and going clockwise, the bays are named W, X, Y and Z. The cards are designed such that any Z card can fit anywhere in the Z bay, but a Z card can't be used in the Y bay. This is because each bay has unique connectors for each of the card types. Cards can be extracted from a bay by simultaneously pulling on the 2 holes near the front of that card. At the moment I use a couple of hex keys to do it, but I might 3D print a little lever that fits in the holes and pushes against the surrounding frame. Also worthy of note while we're down here is the backplanes. These connect all the various buses of the 5 cards in each bay together. I've got a mix of implementation styles going on at the moment. Originally I used a ribbon cable rippled across some stacking headers, but they've been proving temperamental at times, and so I've recently moved to PCBs here too. The one in the Y bay is a handmade PCB, but these will all get replaced by proper PCB eventually. I've also got an idea for menting to replace all the basket weaving currently passing the buses between backplanes, but I'll save that for a future blog post. Let's take a closer look now at each of those bays, and I'll go in alphabetical order, starting with bay W. First up is a sequencer, which is spread across 2 cards due to the number of relays and connections required. The diagram on the right shows what each of the card LEDs actually mean. Here we can see the 24 states of the finite state machine, the FSM, on the left, and the derived sequencer pulses A through to T on the right. The FSM can be aborted at state 8, 10, 12 or 14 for shorter instructions, and the current abort, if set at all, is shown on one of the yellow abort LEDs. Next is the controller, again made up of 2 cards, which uses a sequencer pulses to operate the appropriate control line at the correct time according to the current instruction class being operated. Note that the dark grey dots in the diagram signify where future LEDs will be placed as the cards gain more functionality. Note also that the real card to the left has all of its LEDs, as it's easier to solder them in one go than in sections. But none of the LEDs shown in grey in the diagram will be lit currently. Finally for this bay we find the decoder at the bottom as a single card. The decoder takes the current value in the instruction register and decides which instruction class that represents so that the controller knows what to do. As mentioned earlier, I fully completed this card even though the increment XY, store, load, MISC and move16 instruction classes aren't soldered out on the controller cards yet. Moving on to the next bay, bay X, we find the instruction register, incrementer and program counter. The instruction register is effectively an 8-bit register that is loaded from the data bus and constantly outputs whatever value it's holding onto the instruction bus. From there, the decoder and controller pick that value up and do their bits and bobs. Likewise, the program counter is just a register too, albeit a 16-bit one this time. It can be loaded and selected onto the address bus and holds a reference to the current or next instruction in memory, depending on where we are in the instruction cycle. The incrementer is another double height card and is made up of a 16-bit half adder on the lower card and a 16-bit register on the upper card. Together these allow you to increment a value on the address bus by 1 over a 2-step process of loading the register via the adder and then selecting the value back onto the address bus. Note that all cards seen in this bay use my previous wire wrap construction method, and at some point I'll likely convert them all to professionally manufactured PCBs. There's one empty slot in this bay, and this is where the computer's clock will go once designed and constructed. If I'm being historically accurate, I'll make the clock from several resistor capacitor RC networks feeding relays to form a ring counter, but I'll also likely add the crystal oscillator option shown earlier in the upper enclosure so that the clock speed can be easily varied if wanted. The next bay is bay Y. At the top we have the memory unit, which is our last double height card. Using the first 15 bits of the address bus, we can pick a location in the 32K memory chip and then either load or select a value from to the data bus. There's also a toggle switch at the right of the upper card which disconnects the memory chip, which can be useful if investigating an issue elsewhere in the computer. The remaining 3 cards are all 16-bit registers and are based on an identical PCB design. The XY register consists of 2 8-bit registers, X and Y, joined together to form a 16-bit pair. This register has the most freedom and can be loaded and selected on both the data and address bus. The M register likewise consists of 2 8-bit registers, M1 and M2, and although can be loaded and selected onto the data bus, it can only be selected to the address bus, not loaded. Finally, the J register is the most restrictive. Its J1 and J2 8-bit registers can only be loaded from the data bus, and the 16-bit value that then forms can only be selected onto the address bus. In typical use, the XY register is usually used to store a return address from a subroutine or to store an index in memory. This is where the 16-bit incrementer can be useful if you want to bump that value up by 1 if, for example, we're indexing an array of values in memory. The M register is typically used to store a location in memory ready for loading or storing a value there. Finally, the J register typically gets used to store the memory location of a line in a program that we might jump to assuming an ALU condition register is set. Effectively, this is where we do our branching from. Finally, we arrive at the last bay, Bay Z. This is where the oldest cards in the computer are found, dating back to 2014, so 6 years old at the time of making this video. Again, I'll no doubt eventually replace these wire wrap cards with a newer PCB equivalent at some point. The first 2 cards are 8-bit register pairs, A and D at the top, and then followed by B and C below that. These can all be selected and loaded from the data bus, but the B and C registers are special in that whatever value they're holding is permanently wired to the ALU cards. The BC bus traverses the backplane, and later on I might bring that out on a ribbon cable to drive other displays and whatnot. The ALU is spread over 3 independent cards. At the bottom is the logic unit, which takes the feed from the B and C registers and simultaneously calculates all 5 logic results. Note that the NOT output ignores the C register input, of course. Above that is the arithmetic unit, which can either add the B and C feeds together or alternatively take just the B feed and increment it by 1 via the carry in line. If the calculator value exceeds 8 bits, it'll set the carry out flag. Similarly to the logic unit, this card will, by default, calculate B plus C at all times, and then only switch to increment when specifically requested. At the top is the control unit, which will be activated by the ALU function code being set, and that will then be decoded to determine which ALU result is required. In the case of a logic function, it'll ask that card to gate the appropriate result onto the data bus. In the case of an arithmetic result, it'll gate the current result for an add, or switch to an increment and gate that instead. Whilst the result is being gated, the control unit loads its onboard 3-bit condition register. For a signed result, it will check if the 8th bit of the result is set. For a 0 result, it ripples power through a series of 8 relays to ensure all bits of the result are off. Finally, the carry flag is just set directly from the arithmetic's carry out. Right, so that's pretty much it for the tour. If you do have any questions, please feel free to pop them in the comments and I'll do my best to answer them. Needless to say though, there's plenty more information about this computer in my other videos and on my blog at relaycomputer.co.uk. My next video will be the last in this series, and I'll demonstrate loading and running the program I created in my last video. Once that's done, I'll get back to constructing again, and there's still plenty more to do. I think I'll focus next on getting the load store instruction wired out and finish off the move 8 instruction so that it includes the M1, M2, X and Y registers, as then I should be able to tackle a 16-bit version of the Fibonacci program that also writes the results to memory. I'm also keen to hear what you'd like to see, so if you have any ideas you'd like to share, please pop them in the comments too. Right, well that's it for now. Thanks again for watching and see you next time.